Assalamualaikum and good day everyone. We are from Group 4 and today we will present our topic, Technological Innovation in Lakis for Sustainable Industrial Application, highlighting how Lakis technology can promote a greener and more sustainable industrial process.
My group member are Muhammad AIDEL MUQRIZ bin SYARI ANWAR, Nur SYAZWANI binti ALANG, Nur RASYIQAH ALYA binti NAZRIN, and myself Nur SYAFIEKAH binti KOSIM. Lakis is multi-copper oxidase enzyme that can be produced by fungi, bacteria, and plants. This enzyme catalyzes the oxidation of both phenolic and non-phenolic compound by using oxygen as the electroacceptor and producing water as the byproduct. Lakis has gained significant attention because it is widely used in many industries, especially wastewater treatment, textile dye degradation, and paper processing. Compared to conventional chemical treatment, Lakis is considered environmentally friendly because it reduces the use of hazardous chemicals and supports sustainable and green industrial processing. Next, I will explain the current industry status of Lakis enzyme technology in Malaysia. Malaysia has an emerging biotechnology sector and there is growing interest in the use of industrial enzyme, particularly for environmental application. Currently, Lakis is mainly applied in environmental industry. Malaysia also has abundant agriculture biomass resources that can be utilized for Lakis production. Example include palm oil, empty fruit bunches, rice straw, sawdust, and sugarcane bagasse. These materials are already available in agriculture waste and can serve as low-cost substrate and enzyme production. In terms of application, Lakis is commonly used in wastewater treatment, textile influence degradation, agro-industrial processing, and environmental remediation. This application help in reduce pollution and improve environmental sustainability. However, several challenges still exist include high production costs, low enzyme yield, limited commercialization at large scale, and enzyme stability issue. Despite this challenge, Lakis technology has strong future potential in Malaysia through biomass waste valorization, circular economy implementation, improved fermentation technology, and sustainable industrial growth.
Now I will explain about technology spotlight. Lakis is mainly produced by white rot fungi and acts as an eco-friendly industrial biocatalyst. One of the main advantages of Lakis technology is that the process operates under mild operating conditions, require lower energy consumption, and produce fewer toxic byproducts compared to conventional chemical treatment process. Therefore, Lakis is considered a sustainable industrial process that supports green biotechnology development. In this project, Lakis produced from white rot fungi such as Transmitis versicolor is selected as the sustainable enzyme source. These fungus naturally secrete extracellular oxidative enzymes that are capable of degrading lignin and other complex organic compounds efficiently, making it suitable for industrial enzyme production. Agricultural biomass waste are used as low-cost and renewable substrates for Lakis production. The use of this biomass material supports waste valorization and helps reduce environmental pollution caused by agricultural waste disposal. In Malaysia, large quantities of lignocellulosic biomass are generated annually from palm oil industry, making agricultural waste a suitable substrate for sustainable enzyme production. Overall, Lakis technology supports Sustainable Development Goal 9, which focus on industry, innovation, and infrastructure. This slide shows the simplified process flow diagram for industrial Lakis production from agricultural biomass waste. First, agricultural biomass waste is collected and used as the fermentation substrate. The biomass undergoes size reduction using a hammer mill to increase the surface area and improve microbial accessibility. Next, the processed biomass is mixed with liquid nutrient medium and transferred for sterilization to eliminate unwanted microorganisms and prevent contamination during fermentation. After sterilization, the substrate is inoculated with the white rot fungi before being transferred into tray bioreactor. During fermentation, parameters such as temperature, pH, aeration, and agitation are carefully controlled to maximize lactase production. Copper sulfate is also added as an inducer to enhance enzyme synthesis. After fermentation is complete, the culture probe undergoes downstream processing. Filtration using a filter press removes fungal biomass and solid particles, while ultrafiltration is used to concentrate and partially purify the lactase enzyme. Finally, stabilizing agents such as sorbitol are added in the stabilizer tank to improve enzyme stability and shelf life before the final lactase product is packaged for industrial application. Downstream processing of lactase consists of three main stages, which are lactase production, enzyme purification, and enzyme formulation. First is lactase production. Lactase is commonly produced through submerged fermentation or solid-state fermentation using white rot fungi such as Stramyces versicolor and Pleurotus ostriotus. Agricultural biomass waste acts as the carbon source for microbial growth and enzyme production. The second stage is enzyme purification. Filtration is first performed to remove solid residue from the enzyme solution. The filtrate is then subjected to centrifugation for further clarification. Ultrafiltration membrane technology is commonly used to concentrate the enzyme and remove low molecular weight impurities. Additional purification methods such as ammonium sulfate precipitation, dialysis, and chromatography may also be applied when higher enzyme purity is required. The final stage is enzyme formulation. The purified lactase enzyme can be formulated in liquid or powder form depending on industrial requirements. Stabilizing agents are added to improve enzyme stability during storage and transportation, while spray drying is commonly used for powder formulation to increase shelf life and simplify handling.
We present about technical innovation. First of all, the standard fungal extraction face low yields and poor thermal stability. To solve this, we propose replacing conventional method with genetic engineering using high-density fermentation hosts like Pichia pectoris or Aspergillus niger to maximize expression. Furthermore, to tackle the issue of enzyme loss in wastewater, we can introduce immobilization using magnetic Fe3O4 nanoparticles. These allow us to apply an external magnetic field, recover the lactase, and reuse it across multiple conventional cycles. Finally, by using error-prone PCR to introduce structural protein mutation, we drastically improve the enzyme resilience against extreme industrial temperatures and pH levels. Next, looking at our safety, ethical and societal responsibilities, because our optimized lactase rely on genetically modified microorganism, strictly biosafety level 1 protocol must be monitored to guarantee complete environmental containment. For wastewater treatment, we must also replace toxic synthetic mediators like ABTS, which can degrade into dangerous cyanide, with eco-friendly natural alternative. Ethically, any implementation in Malaysia must strictly comply with the Malaysian Biosafety Act 2007 and undergo full environmental risk assessment. Socially, shifting to organic lactase eliminates the community exposure to hazardous chemical sludge, ensuring discharge effluent are completely non-toxic and safe for surrounding public waterways.
Next, I would like to discuss some of the challenges in the industrial implementation of lactase technology. Although lactase has demonstrated significant potential in applications such as wastewater treatment, textile processing, and biomass valorization, several barriers still limit its widespread industrial adoption. Firstly, from a regulatory perspective, the absence of standardized guidelines specifically designed for enzyme-based technologies remains a major concern. The approval process involving recombinant microorganisms and enzyme-based treatment system can be lengthy and complex. As a result, industry may be reluctant to adopt lactase technology due to uncertainties regarding regulatory compliance and long-term environmental impact. Secondly, there are several technological challenges associated with scaling up lactase application from laboratory studies to a real industrial environment. Most research findings are obtained under controlled conditions that do not accurately represent industrial settings. Factors such as fluctuation in temperature and pH, the presence of inhibitory compounds, and variation in pollutant composition may significantly reduce enzyme performance. In addition, maintaining stable enzyme activity over extended operational period remains difficult, which limits the commercialization of lactase-based systems. Another important issue is the socio-economic aspect. Implementing lactase technology often require modification to existing infrastructure, investment in specialized equipment, and additional workforce training. Consequently, industry may prefer to continue using conventional chemical methods that are already well established and economically predictable. The limited availability of skilled personnel in the industrial biotechnology may further slow down the adoption process. Lastly, there is still lack of comprehensive techno-economic assessment evaluating the long-term cost-effective and market competitiveness of lactase technologies. Without sufficient economic evidence demonstrating their practically under a real industrial condition, decision makers may hesitate to invest in enzyme-based alternatives. Although lactase has already demonstrated considerable potential in supporting sustainable industrial processes, continuous improvement are still necessary to ensure its efficient implementation on a larger industrial scale. Firstly, future developments should focus on enhancing lactase production system. Advance in heterologous expression and protein engineering provide opportunities to improve enzyme yield, catalytic efficiency, and operational stability. This improvement could reduce production costs while enabling lactase to function effectively under extreme industrial conditions such as high temperatures and varying pH level. Secondly, the expansion of environmental application is expected to become an important research direction. Lactase has shown a great potential in degrading phenolic compound, synthetic dyes, pharmaceutical, and other emerging contaminants. Therefore, wider implementation of lactase-based treatment system may contribute to reducing environmental pollution while promoting greener industrial practice. Another promising direction is the integration of lactase technology into a circular economy strategies. Agriculture, biomass, and agro-industrial residue can serve as sustainable substrate for enzyme production. This not only minimize waste generation, but also convert low-value material into a valuable biotechnological product, supporting resource efficiency and sustainable production system. Lastly, advancement in immobilization material and reactor technologies may significantly improve the practical application of lactase in industrial settings. Novel supports, including nanocomposite and metal organic framework, have demonstrated potential in enhancing enzyme stability, reusability, and operational lifespan. This improvement could ultimately reduce operational costs and increase the competitiveness of enzyme-based technologies.
That's all from our group. Thank you for watching.